All right, our next speaker is the very Jim Blinn.
So I'm going to talk about, in a sense, work I did at Utah as a kind of an ode to the frame buffer. Once Jim Kujia got the first frame buffer going, and I was actually the first person to actually get a pixel on the screen with it, I said to myself, I can really do stuff with this. So I set to work putting together Butong Fong's lighting model, Ed Catmull's surface rendering model, and Martin Newell's models, Ed Catmull's surface rendering algorithm and Newell's models to render things. And the neat thing about the frame buffer is that it gave you immediate feedback, which they didn't have so much before then. So it was fascinating watching these algorithms actually run in real time. I don't happen to have a video of Catmull's algorithm running. This is actually a video I did some years later of Warnock's algorithm, but you can kind of get the sense of it. Warnock's subdivided the surface, and Catmull subdivided the patches, but this happened to be two databases I happen to have laying around that I did, and to see that, and just kind of like the fractal evolution of the image as you watch that, it was just fascinating to sit and watch on. And I can kind of skip forward a little bit to this, and kind of you get the idea there. So the whole thing has to do with calculating the brightness of something with the light coming one direction, bouncing off a surface normal, and hitting the eye, and how much light you get is some function of the vectors n, l, and e. The diffuse component is typically n dot l. That's fairly simple, but the trick is, how do we calculate the specular component? Warnock did something with light at the eye source, but actually Fong was the first one to do that. Fong, sadly, is no longer with us, but he has gotten some immortality by becoming a character in the first computer graphics TV series called Reboot. But the idea here is that he said, light comes in from L, bounces off N, and most of it's going to go in this direction R, equal angles of incidence and reflection. And so the distance E is from R, that is E dot R, tells you how much specular area you've got, and you rate it to some power, kind of craft the function to make it fit. So when I went to implement that, the question then is, how do you calculate R given N and L? And I found I didn't understand how Fong did it. It was kind of complicated and odd, so I decided, let me think about this again. Let me try something different. I'll try, suppose we have a vector halfway in between E and L, which a half vector I called, which you can calculate easily by E plus L and then normalize it. So if the normal vector lies along H, then equal angles of mirror reflection, then you get the brightest highlight. The distance you are away from that gives you as the highlights fall off. So this time, with this, the specular is a function of n dot h raised to some power. So the neat thing about this is that h is constant if E and L are constant, which is typically an approximation that you use. So you only have to calculate h once for the scene, and then just dot it with the different normal vectors that you see for the different shapes you've got on the screen. So these are the pictures you get there using some of Martin's models and a mathematical object from Nelson Max from Carnegie Mellon. And this is the highlights that you get off of that. And then adding Catmull's texture mapping on top of that, you get the highlights stay put as the thing rotates, since it's circularly symmetrical. And so the texture moves, but the highlights stay put. So this models real life pretty well. I'm going to go back. Just to let you know, this is what the picture looks like on the frame buffer. The bottom half is the Z buffer. It's a Z buffer algorithm, 2 bytes per pixel. And then the upper left-hand corner is 256 by 256 resolution image, and then the other right is the texture. And so all the images you see were actually created by making four pictures shifted and then mosaic together after the fact. So you get a 512 by 512 image. And then, so what else can we do with texture mapping? Let's make the shininess change as a function of a texture. So with the sphere there, you can see that it's shiny inside the squares and matte in the lines in between. And then in the dark area, you can see that the squares are darker and the diffuse parts are shinier. And that's actually a real thing you can see in real life if you do it. And then there's kind of a random specularity texture for the green picture, which looks interesting, but who knows. While we were doing this, we made pictures of some things that we were printing out, and we made a picture of the real teapot. And it was sitting in the photo lab, and my office mate came in and said, "Boy, you guys are getting pretty good at your synthetic images here." But I noticed there's a little problem you see here. I'll zoom in near the handle. You got some glitch there. And I said, well, oh, this is the real teapot, and you're seeing the reflection of the handle in the body of the teapot. And I thought, nobody's ever going to be able to do that. Of course, you look on Wikipedia now, and that's what you get. So Martin came in one day and said, I just had this idea in the shower. Suppose you run the light ray backwards and bounce off the nova vector and project it out into the world. And if you have a map of how bright things are in different directions in the world, then you can generate an image with reflections in it. So I went down and implemented that. And I had to calculate now what is W as a function of E and N, which is that. And so a few pictures using different models like that of reflection of an environment map. And it turned out that Turner Whitted took this image, and he was so fascinated by it that he inspired him to go off and create ray tracing. So comes out of this. And I finally realized that calculation of W as a function of E and N is the same as what Fang actually did, a function of R as a function of N and L. So that's how he did it. There's a simple way of showing that. N dot E times N is projection of E on the N vector. Take two of those, subtract off E, and you get W. Nice thing about this is if E and N start out unit length, W is guaranteed to be unit length 2. We're trying to economize arithmetic as much as possible. Now I wanted to make some images of some science things. Here's a molecule of water. I wanted to make the things look kind of fuzzy, but it didn't look very fuzzy, and it was kind of got me thinking, how do we make something that looks wrinkled or fuzzy? And by looking at some real objects, I realized that the wrinkles in it came from not so much the fact that it's displaced, but the fact that the normal vector is kind of nudged slightly from one direction to the next. So I had to figure out a way of doing that, and after several false starts, I figured out how to do that with you paint in basically like an altitude map of the bumps that you want to see on there, and with some calculation of basically the gradient of the function will tell you how much to modify the normal vector. And after a few false starts, I came up with this image here. I called it normal vector perturbation. Came down as bump mapping by people with better English than me, I guess. But the thing is, I want to make sure this worked when the thing moved around in space rather than just in a still image. So the key thing is, does it animate? Now it turns out that ENS frame buffer had this nifty mode. Actually, doing an animation of this thing would involve taking movies and film and so forth, which is kind of an unpleasant process. But there's a mode that you could throw the frame buffer into that if you made 16 individual frames, you could have it zoom in. There's a little microprocessor that's basically going through the memory, synthesizing the video signal. Change the counters properly, and it'll have it zoom in on one of these things, and then scan it out, and then you could change the starting address for the next one, and so forth. So you basically have a little 16-frame flip book. So in preparing this thing, I was able to go through and take this image that I'd been carrying around with me for the last 50 or 45 years, and dice it up into 16 individual frames, and run it through a GIF encoder. And what you're going to see next is what I first saw seen for the first time since 1977. This was so cool. I was literally dancing around the room. This was so cool. And so we then make, stucco teapot and teapot that's been hit with a hammer, leather donuts, various other bump mapping things. A little precursor to going to JPL. But then I was thinking, I want to get to better reflection models to see what else I could do. It occurred to me that there might be some literature on how light reflects off of surfaces. And since we didn't have Google those days, that involved my going to the engineering library and spending 2 to 3 weeks just kind of randomly walking up and down the aisles, looking at the backs of all the bound volumes of the journals and so forth of this. And the first kind of score was the Proceedings of the Illuminating Engineering Society. Well, that sounds promising. Let's pull one back and flip through, mostly about how to make lighting fixtures, and flip back. And finally, I scored with this, effect of the variation of incident light. And this had experimental data. This was from 1910. And I thought, well, I can, digitize this and use some sort of cable lookup, and that would give me some real data. But I kind of kept looking around and looking for other sorts of things. Here's my next score, luminous spectral reflections of snow from the University of Minnesota. They know snow. Keep looking around. Now here's the real score. Theory, that's nice. Off specular reflection, that sounds intriguing, from roughened surfaces by somebody named Torrance and Sparrow. And this was their diagram. Now you'll notice that they have the incident beam here, L coming in from the upper left, and the normal vector, E is reflected from the eye. But this extra vector here is H. They were modeling the surface as a whole bunch of microscopic facets pointing in different directions, most of them along N, but less and less of them different directions for L. And so when you were calculating the specularity, you were measuring how many of those microfacets were at a particular direction. So this was theoretical justification why H is a good thing to use for the specularity. So this is the net lighting model that I got out of that. This is also an example of what presentation slides look like before postscript. And the D was the distribution function of the angle of these different things. And it's n dot h to the n, and you raise it to different powers, and you'll get these different things. That's what we were doing with Fong and with my original thing. But in the Torrance Sparrow model, they were dealing with angles because they weren't so concerned with computational efficiency. And so they used models, as one does, it was a Gaussian angle, as a function of Gaussian of the angle away from the normal. But if you modify that to see what actually that comes out with, you take the arc cosine of that and plot it. It turns out that these curves are remarkably similar. So this gives an experimental justification of why n dot h to the power, it gives a good approximation to a Gaussian distribution of angles for these different surface facets. The other factor with G, which is thing coming in from, if the light comes in from a different direction, these facets kind of mask themselves off. So there's 3 different cases that can happen. No interference, some of it's intercepted, some of it's reflected. And Torrance had a way of calculating how much effect this had on here. Again, using the angles, there were 3 different regions in this 2-dimensional space and 3 different equations for that. And this is what you had to calculate in order to get the thing. My God, we don't want to calculate that in every pixel. So I spent 2 or 3 weeks playing with trig identities, trying to simplify this, and didn't get anywhere. But then I went back to the geometry of it and figured out that, gee, the GB and GC, either masking or shadowing, can come from just n dot h, and those have turned into squares here for some strange reason, but that's supposed to be a dot for n dot h and so forth. So much simpler calculation, and you don't have to figure out which region you're in. You just calculate all 3 of these things and take the minimum of that. That gives you the geometric attenuation factor. Finally, the Fresnel factor is, this is what you get out of the textbook, and by mashing around that a little bit, the idea is we're crafting things so that it's a easy to calculate function, but has some theoretical justification to it. And so this is, again, turning this into something that's just dot products. We like dot products. They're cosines. We don't like square roots and so forth. Again, the thing about the Fresnel factor is this also is a constant for E and L, so you only have to calculate that once per frame. So here's a comparison between Fong and the Torrance Sparrow. You can see there's actually a slight difference between the Torrance Sparrow first one and that, but the bottom right picture there shows the specular reflection that you get out of that. So next is in Cornell, Don Greenberg and his student Rob Cook were interested in pursuing this thing, and they read the paper and said, let's play around with this. And Don said, that name sounds familiar. Ken Torrance is a faculty member here at Cornell, but in a completely different department. So Rob went over there and talked to him and pestered him and saying, with enough questions, Ken Torrance finally came over, saw how cool computer graphics was, and spent the rest of his career doing computer graphics things. So this ushered in an era of computer graphics kind of plundering the literature of the physics community for lighting models. I did that a little bit myself for the ring lighting for Saturn, got 6 different articles and synthesized something for clouds of particles and the density for showing the light reflection from Saturn from the top and the bottom. But I got the ultimate compliment by I'm now a menu item in various commercial animation systems. And people come up to me at SIGGRAPH and say, oh, I use your lighting model. And I say, thank you, I'm glad it's useful to you. One guy came up and said, oh, Blinn, oh, that's a person? I thought that stood for bilinear or something. So. Anyway, one of my great nephews was playing around with this computer game with a car lighting, and he was admiring the surface reflections on it. And his mother said, you know, your Uncle Jim figured out how to do that. So I got points for that. But I want to close by one thing. 26 years ago, my wife and I had a son, Herman Kepler Blinn. Herman is unfortunately on the autism scale, so it's a little difficult to understand how he sees the world and what's going on. But I want to show you a little 2-frame animation that he did completely on his own from 2 different images that he found on the internet. This is the first animation. First image, teapot. Then he put his finger up on the screen and rubbed the teapot. So, thank you. Mm-hmm.